The next topic that we're going to discuss is rigid offsets. And SRAM actually allows for the automatic generation of these rigid offsets. Now, for a little bit of background, SRAM uses the concept of centerline modeling. And what this means is that the analytical member that's representing, for example, an I-beam is going to be aligned with the neutral axis of the structural object. So there's our beam, and then the actual member would be going along the neutral axis, just like we see here. And we assign a section property to that neutral or to that member that represents the section size and properties and so on. But we don't actually model that section with members, although there are ways of doing that within SRAM. This works fairly good for most applications, but an issue can arise if you have members that are connecting to the flanges of other members, or if you have large section properties relative to the length of the member. So if we use an example of a frame like we see here, but we have fairly large section properties, you'll notice that the members themselves will go until they hit the next member, basically. They go from joint to joint. But the section properties also do the same thing, and we run into an issue with realism where if we were to build this, the beam itself would either be resting on top of this column or connected to the inside flanges. But it wouldn't be modeled like we see here, or built like we see here. So what do we do with these areas highlighted there where we have the overlap? Well, SRAM will be able to generate for you rigid offsets. And this is always at the discretion of the engineer, whether or not it's necessary and whether or not it's worth their time to do this. But it allows you to basically use the structural model offsets to consider the effects of those offsets, and it's up to the engineer to determine if they're significant or not. So again, if we have an example like this, and we look at the center lines, we can generate this little green section to be a rigid offset because this beam is coming into the column. It's not actually going to be connected to the center line. It's going to be connected to the outside flange. And so SRAM will be able to determine what that half of the neutral axis depth is and make that section a rigid offset. Basically, it's not going to behave elastically, it's going to behave rigidly and transfer the forces to that neutral axis from this point on. And this is quite useful if you're considering using members where the size of the connected elements become larger in proportion to their length. And it's not that hard to do, so we'll go through an example here really quickly. Now this example, if I just actually render the elements, I can show you what they look like. So I'm just going to turn on the render button here. And maybe just to make it a little bit easier, I'm going to change some of the render properties. So right now we, by default, will shrink these members from their ends by 25%. So I'm just going to make this length shrink factor 1.0. I'm going to add a little bit of opacity as well. And now if I just look at this front on, you can see that this darker area is overlapping. And we can assume that in many cases, the actual steel I-beam isn't going to be traveling all the way to the neutral axis of the columns. And let's look at this a little bit more as well. So we know that, first of all, at the bottom of this column, we have fixed supports. But the actual beam itself has releases, moment releases. So we need to consider that if we were to change the location of our rigid offsets. And if I go to the loads window, we can also see that we have one load case. And this load case has two different loads. We have a UDL, a 20 kilonewton per meter UDL, and a 200 kilonewton concentrated load at the center of the beam. So we would need to keep those in account as well when we're actually modeling these rigid offsets. So I'm going to go back to the geometry window for this, and I'm just going to use the default isometric view, uncheck the display of my releases and my supports. And we have this tool near the bottom. It's called the rigid offsets tool. It looks like a blue bent angle. I don't know how to describe it. I guess you could say it's meant to look like a rigid offset. So I don't want to use that word. If we left click on this tool, we can see that the data bar updates with some different commands that we can use to customize our rigid offsets. This can be defined either graphically within the data bar or numerically in the member spreadsheet. But we also have this option here to generate rigid offsets ourselves. So we can left click on this option, and you can notice here when I hover my mouse over this, the tooltip appears. And it says generate rigid offsets from neutral axis of vertical member to face of column. Remember what the column sections look like? They're quite large. So if we do this here, I'm going to generate the rigid offsets. And you can see that we have some control. Well, this has actually generated two different rigid offsets for me, which may not necessarily work for my application. However, if I don't like what it's come up with, I can always just use the same tool, the rigid offsets tool, and hold down Control on my mouse and remove it from the ends of the members that I'm not interested in. So maybe I just want it on my beams. That's perfectly fine. I can configure it any way I like, but this will just help me with the generation of that particular element. I can also see here that it's maintained those rigid offsets or maintain the releases on my model. And if I go to Options and then to Releases, you can see that these releases are now at the end of the elastic component of my beam, not the rigid portion, because that's where the member end moments are going to end, essentially. And if I go to the Loads window, we can see that this elastic portion of the beam has also been shortened according to the loads. So now, if you think of it as I have my beam spanning between those two columns, it's not going to be quite as long as I originally predicted. So we will get different moments and different shear forces, but it's more representative of the beam that we're actually working. Now I'm just going to go through an example here where we run the analysis, and I'm going to look at comparing the two results. So this is the analysis result if we have the rigid offsets considered, and we're looking at just the clear span between the two columns. So I'll press OK to run the analysis. Ran without issue. And what I'm really focusing on right now is let's just look at the moments in our model. Toggle off the display of our loads. And I can see here that I'm maxing out at around 680 kilonewton meters into my moments, although I'm getting some moments in the column as well. So there is, just keep this in the back of our mind, 680 and about 90 kilonewton meters in the columns. We're not getting any moments in these rigid offsets, they're just transferring the forces and moments to our columns. Now I'm going to go back here and I'm going to delete these rigid offsets. And I'm going to rerun this analysis and see what effect that has if the entire beam's length from center line to center line of the column is considered elastic. We get a clean solution. And now if I look at the moment diagram, I can see that I'm getting a higher moment within the beam, 774 kilonewton meters. And mostly this can be attributed to the fact that I just have a longer length of beam that this load is being applied to, as we can see here. In addition to that, if I look back at the moment diagrams, you can see that I'm not getting any moments within these columns because there is no eccentricity between the connection of the beam and the center line of the columns. So the forces aren't inducing any moments. Now, if I wanted to look at this information graphically, or numerically rather, I can go to the spreadsheet window, and I can go to the member spreadsheet, and I can see we have these rigid X1L, X2L options within the spreadsheet. So this is basically a ratio of the member length. And you can see here, if I just go with the pin option, and if I say 0.1, and rigid X2 over L as end joint, I'll say 0.1 as well, so 10% of the member length. Now I can go into the geometry window, and I can see what effect that has. And you can see here that it's generated basically 10% of the offset of the member length as a rigid offset for me. So we have control over this in a lot of different ways.